this example is actually really neat because it deals with something called a dimpled limacon. And that C is whatever that C looking letter is in French. It's a limacon. I don't know. I've never learned to pronounce it super correctly. And this isn't the best figure. But what we're going to do is we're going to say, all right, I've got r equals 9 plus 6 sine of theta, and I need the piece that's below the polar axis. So the first things first, how did I graph this thing? So there's a couple of things that I did that helped me out a lot. And I say a few. The first thing is I know what a dimpled limacon looks like. All right, that helps a lot. But even if I didn't, there are some really, really clean things that help me out. The first is that I know that sine is bounded by -1 and 1. So right, so sine never gets larger than 1, and it never gets less than -1, which tells me that this expression here never gets bigger than 6, and it never gets smaller than -6, which means when I add it to 9, it's never negative. That means that no matter what, for any angle, I'm always have a positive value. That means that I don't have to worry about it looping back in on itself and things like that, because it's never going to go back to 0. It's never going to go negative. That's the first thing. The second thing is picking convenient values. So I know when theta is 0, that the sine term disappears. So I just have 9 at an angle of 0. What I also know is when theta is pi over 2, the sine of pi over 2 is 1. So in that case, this just becomes 9 plus 6, or 15. What I also know is when theta is pi, sine of pi is 0. So that makes this go back to just 9 again. And then finally, I know when sine is 3 pi, or when theta is 3 pi over 2, sine of 3 pi over 2 is -1, so it becomes 9 minus 6, or 3. That gives me 4 big points, and I know that I have to increase up to that. So I also know, by the way, that I could use some calculus here. Now, this is something we haven't discussed yet, but why not talk about it? We're already here. So I have r is 9 plus 6 sine of theta, which tells me that dr d theta is 6 cosine of theta. Why does that matter? Why does that matter? Because for theta in the first quadrant, then, theta in the first quadrant, this is going to be positive. The dr d theta is positive. That tells me that the magnitude of r is increasing. So this should not only be 9, it should be getting larger, 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 right? Which actually tells me that this graph is kind of bad, because this makes it kind of look like r comes back in. It's actually getting larger and larger further away, all the way up to 15. And then in the second quadrant, cosine of theta is negative. So that tells me that my r should be getting smaller and smaller and smaller until I come to here. At which point, I'm now in the third quadrant. In the third quadrant, r should be getting even smaller, in the third quadrant, cosine's still negative, so it should be getting even smaller. So this is exaggerated. It actually shouldn't do this. It should kind of do something like that. It's a little more difficult, but the idea is your r is getting smaller still, all the way down to this 3, and then it increases again in the fourth quadrant. So using a little bit of calculus, I can sketch this. I can use curve sketching techniques to kind of help me out. Even though I already kind of know what a dimpled limacon is supposed to look like, even if I didn't, this would be useful. So calculus can help you, right? Even that. Introductory calculus kind of stuff. Now, what I know I also want is everything that's below the polar axis. So what I'm really looking for is this region. And what's nice is because since we know that that r is positive for all angles, then all I actually have to do is say, well, it's just these quadrants, right? I don't ever have to worry about the fact that I might be worried, oh no, this is related to this angle, but it's a negative r. No, it isn't. Because r is positive, this whole region down here from pi to 2 pi, essentially, from pi to, right, because this point would still be 9, 2 pi. From pi to 2 pi, that's my region. And I've got r. So then I can apply the formula. So I'm going to say, okay. Nine plus 6 sine theta squared d theta. Now this one's going to be a more difficult integral than what we did before, but it's not too bad. So you end up with 1/2 pi to 2 pi, 81 plus 108 sine theta plus 36 sine squared theta d theta. Yuck, right? But then the next thing we're going to do is we're going to apply that the power reduction formula for sine squared, or a double angle identity, depending on how you look at it. And you're going to get 1/2 from pi to 2 pi of 81 plus 108 sine theta plus 18 minus 18 cosine 2 theta d theta. So these can come together for 99. We're going to get 1/2 from pi to 2 pi, 99 plus 108 sine theta minus 18 cosine 2 theta d theta. Now we're ready to take the antiderivative. That's going to be 1/2 99 theta minus 108 cosine theta minus 9 sine of 2 theta from pi to 2 pi. Now the nice part is sine of 4 pi, which is what I plug in, and sine of 2 pi, this goes away. So this term doesn't even matter. Which then gives me 1/2 198 pi minus 108, because cosine of 2 pi is 1, minus 1/2 99 pi minus, or plus 108. Right? Because this is minus 108. So cosine of pi is -1. So these cancel. So then I have, so this minus that is 99 pi, but it's 1/2. So it's 99 pi over 2. And this is 108, and that's 108 minus 99 pi over 2 minus 108. Sorry, I had to check. Just 99 pi over 2 minus 108. Now, that is the right answer. But I do want to talk a little bit, just a moment, about whether this is right. So I looked at this and I went, is that even correct? And you should do that too. You should always look and say, is this correct? Well, 99 pi over 2 is larger than 108. At first I was thinking, oh no, it's not larger than 108. But of course it is. 99 is smaller than 108, but pi is a little bit bigger than 3. So pi over 2 is a little bit bigger than 1/2. And 99 is almost 100. So a little bit bigger than 1/2 times a little bit smaller than 100 is about 150. 150 minus 108 obviously is positive. The reason you want to do this is because when you're getting this kind of area like this in polar regions, you need a positive area. It's like the region, a shaded region between curves when you're doing it with algebraic functions. It doesn't make sense if it's negative for what we're trying to do here. So if you're doing these types of problems, you end up with something negative, you've probably done something wrong. So do yourself a favor and self-check when you do these types of problems.